In this section, we're going to talk about the calculus involved with polar coordinate systems. So in order to do this, what we do is, instead of working directly with polar coordinates, we can switch back and rewrite a polar function as a set of parametric equations. The way that we do that is through this relationship right here. So we know our basic transformations from polar coordinates into rectangular coordinates. So x equals r cosine theta and y equals r sine theta. Now, if we think of these as x and y as a set of parametric equations, then what we would have is effectively like x of theta, try that again, x of theta equals r cosine theta, and y of theta equal to r sine theta. Now the only issue here is that r is a variable, but it's not with respect to theta in this case. The only input variable that we have for x and y is theta. However, we also know that r is a function of theta. So r itself, might look something like r of theta equals 2 sine theta, for instance. So it's a function itself of theta. So what we can say is r equals some function of theta, which allows us to replace this next statement and say that x and y are each x of theta would be f of theta cosine theta, and y of theta would be f of theta sine theta. And that allows me to write this polar coordinate function and a set of parametric equations. Now, we know how to differentiate parametric equations, and so we can apply that knowledge to get the derivative of these. And thereby, we don't need to develop new methods to differentiate polar functions. We can just switch into parametric equations and use those rules. So, if you'll notice, if I were to try and find dy dx for a set of parametric equations, then what I would do is take dy d theta over dx d theta. Now, here's the tricky part. X and y have been defined as a function of theta times cosine theta and a function of theta times sine theta. Whenever I have two functions that are multiplied, in order to differentiate that, I have to use the product rule. So, using the product rule in this case, what I have is this. dy d theta, so the derivative of the function y with respect to theta would be the derivative of the first function in the product, which is f, times the second function, which is sine theta, plus the first times the derivative of the second. So that's the product rule for the function y of theta. The product rule for the function x of theta becomes f prime theta cosine theta minus f of theta sine theta. And the reason there's a minus in the denominator is because the derivative of cosine results in a negative. And this works for finding derivatives of polar functions, and it works exactly as we expect. So solutions to dy d theta equal to 0 would provide the location of horizontal tangents, and solutions to dx d theta equals 0 provide the location of vertical tangents. And of course, polar graphs are very circular in nature, and so they have lots of potential places for both horizontal and vertical tangents. So let's try an example here. And I have to find the values of theta for which vertical tangents occur on the graph of r equals 2 times 1 minus cosine theta on the interval from 0 to 2 pi. So in order to find vertical tangents, what we need to do is take the derivative of the function x with respect to theta, set that equal to 0, and solve. So the first thing we need to do is find the derivative of this polar function in the x direction with respect to theta. So let's see how that would work. So right now we have r equals 2 times 1 minus cosine theta. And that's essentially, I could think of it as r of theta or f of theta, just to be consistent with the definitions above. But the function x of theta, so this is f of theta times cosine theta, which in this case would be 2 times the quantity 1 minus cosine theta times cosine theta. And then to find the derivative of this function, so I'll call that dx d theta. You don't technically need to memorize the rule that I've stated above, you just need to understand that it's telling you that you have to use the process of the product rule to get the derivative. So to get the derivative of this function, I'll put the 2 off to the side, and then I'll say it's the derivative of the first, so the derivative of 1 is 0, the derivative of negative cosine would result in positive sine. And then it's going to be times the second function, which is cosine theta. Then, according to the product rule, the next thing we do is take the first function and multiply by the derivative of the second. And the derivative of cosine is negative sine theta. So it looks like I have 2 times the quantity sine theta cosine theta minus sine theta and then plus sine theta cosine theta. Then these two terms match, so I could actually combine those into a single and write it as 2 times 2 sine theta cosine theta minus sine theta. And from the remaining two terms, there's a matching factor of sine theta that could be factored out. So I have 2 sine theta times 2 cosine theta minus 1. And the reason I went ahead and did that factoring is because I know in my head eventually I'm going to take this function and set it to 0 and solve. And if I have everything factored, it's easier to set to 0 and solve. So right now I've got 2 factors whose product is 0. So therefore the first factor could be equal to 0, or the second factor could be equal to 0. So I'll just set them both to 0 and solve. So dividing the first by 2, that gives me sine theta equals 0, and the next, this would be 2 cosine theta equals 1, or cosine theta equals 1/2. And then I just need to think of the unit circle in terms of where to find the angle measures theta for which these values apply. So sine of theta, when is that 0? So sine is 0 at 0, and then again at pi. And I'm solving on the interval from 0 to 2 pi because that was the given interval to start with. And cosine theta being 1/2. So it's positive 1/2, that happens in quadrant 1, and that's going to happen at the angle measure pi over 3. And then just thinking about where else the cosine could be positive. So the mnemonic, all students take calculus. It could be positive again there in quadrant 4. So a reference angle of pi over 3 in quadrant 4 would be 5 pi over 3. Okay, so these are the locations where vertical tangents would occur. So we've answered the question here. So it said find the values of theta for which vertical tangents occur. But I'd like to do a little bit more and just make sure you can visually see and understand exactly what's happened here. So first thing is I want to go through and I want to find for each of the different values of theta what the value of r is associated with that. So I found 4 values of theta for which this work. And then r is defined by our function, which is 2 times 1 minus cosine theta. Okay, so just real quickly, if I plug in 0 for cosine, that would be 1. So 1 minus 1 is 0, 2 times 0 is 0. So I have the coordinate pair 0, 0. If I plug in pi, cosine of pi is negative 1. 1 minus negative 1 would be 2. 2 times 2 is 4. So I have the coordinate 4 and pi. If I plug in pi over 3, cosine is 1/2. So 2 times 1 minus 1/2, that would be 2 times 1/2, which is 1. So this would be 1 and pi over 3. And if I plug in 5 pi over 3, well, actually, I kind of know from right here, it's positive 1/2. So I'll get the same result. This will also be 1 and 5 pi over 3. Okay, so let's look at this graph. Just to remind you how to do a polar graph, we would need to check our mode settings. And first off, you should be in radian mode. And then after that, make sure you're not in function or parametric mode, but over here to polar. Because then when you press y equals, you'll get a function of the form r in terms of theta. So this graph is going to be 2 times 1 minus cosine theta. And I'll check my window settings just to make sure that's appropriate. 0 to 2 pi, that's good. I think I'll just do negative 5 to positive 5 on the, whoops, there we go, on the x and the y. So when I graph it, here's what my curve looks like. Okay, so the points that are listed, I have, okay, I'm just going to quickly sketch that graph here, just so we can plot a couple of points on it and see where everything's occurring. So let's see, that goes up 1, 2, down to, and then out to 4. 1, 2, 3, 4. So it looks something like this right here. Okay, so the points that we have, 0, 0 is easy to find. That's going to be right there. Now 4 pi, so we're radius 4, so I need to think about going out on a circle of radius 4, but in the direction of pi. So then 1, 2, so in the pi direction, that's this way, 4 units out. 1 pi over 3, so that would be radius of 1, and then an angle measure of pi over 3, so that would be probably this point, and then 1, 5 pi over 3 would be there. Oh, and actually, I guess my scale's probably off. So it's got to be, of course, these points, the place where the vertical tangents are occurring. Okay, now if we look at 0, 0 came out as a place for a vertical tangent, but if you think about it, slope there wouldn't be vertical. Like you have, one tangent line this way, one tangent line this way, and neither of those really has a vertical or horizontal tangent. So the thing that's happening there is we've got a place where something is undefined. All right, it comes to a sharp corner, and we know that functions are not differentiable at sharp corners, and so that's what's happening there. If we were to solve for horizontal tangents, we would also find 0, 0 as a location of a potential horizontal tangent, but then still be able to kind of rule it out. We would, in addition, find probably right about here, this point, and then probably around here as well, this point right here, whatever those coordinates would be. If we were solving dy d theta equal to 0, those would be the points that we came up with. So this one again, and then these two. So that's what's happening. Okay, in this next example, we'll see how we can actually use what we've learned in order to do some more familiar things in calculus, like, for instance, calculating the slope of a tangent line to a curve at a particular point. Now, this curve, if you'll notice, is a curve r of theta equals sine 2 theta. So this curve is a polar graph, and therefore the process is going to be a little bit different. So what we have to do is we have to break down this into a dy dx, and according to what we've set up, this is going to be y prime of theta divided by x prime of theta. So we need to be able to write x and y in terms of the function theta. So the way we're going to do that is to take advantage of the transformations. X of theta is r of theta cosine theta. And I'm emphasizing that this function is an r of theta and this function is an x of theta, simply so that you know that my derivative is in terms of theta. And then I have y of theta equals r of theta sine of theta. And of course, these are just the same two transformations from even back in trigonometry. If you take away the extra thetas, it looks like x equals r cosine theta, y equals r sine theta, just the simple transformations between polar and rectangular. All right, now in terms of these derivatives, y prime of theta, what we need to do is use the product rule, because y of theta, this function right here, is the product of two functions of theta. So we have to use a product rule to get its derivative. So we could say it's the derivative of the first times the second plus the first times the derivative of the second. And the derivative of the second, the derivative of sine, is going to be cosine theta. Then we need to divide by x prime of theta, which, going by the function for x of theta, which is here, that would be the derivative of the first, so r prime of theta, times the second, plus the first, which is r of theta again, times the derivative of the second. Now the derivative of cosine is negative sine, so I'm just going to go ahead and put a minus right there. All right, and this of course is the same formula that we developed before. It's just a rather hard formula to memorize, but as long as you know the product rule, you can just develop it when you need it. Okay, so we need to substitute in values for r of theta and r prime of theta. So let's go ahead and figure out what r prime of theta is. So r prime of theta, since r of theta is sine 2 theta, just using the chain rule for differentials, the derivative of the outer function sine would be cosine, and then you multiply by the derivative of the inside part. So this will be 2 cosine 2 theta. Okay, now we can substitute these into what we have. All right, so this is going to look like, so r prime is 2 cosine 2 theta, and then that's multiplied by sine theta. Then plus r of theta, which is just sine 2 theta, multiplied by cosine theta. Right? And I guess sometimes I'm using parentheses, sometimes I'm not. It doesn't really matter. R prime is 2 cosine 2 theta, and then that's times cosine theta, plus sine 2 theta times sine of theta. Okay, so we know what the derivative looks like. So this function would give us the slope of this curve at any particular point. Now, the point that we're interested in is the point when theta is equal to pi over 6. So really, we just need to plug pi over 6 into this function. So the derivative evaluated at theta equals pi over 6 is going to be 2 cosine. All right, so 2 times theta. So if theta is pi over 6, then of course, if 2 times pi over 6 would be 2 pi over 6, which is just pi over 3. So I'm going to substitute that as I go through. So 2 cosine pi over 3 times the sine of pi over 6 plus the sine of 2 theta, which would be pi over 3, times the cosine of theta, and that would be cosine pi over 6. And that's going to be all over 2 cosine pi over 3 cosine pi over 6. And I've got a plus here, but I think that was supposed to be a minus. Let me fix that. All right, so that's minus sine pi over 3 and sine pi over 6. Okay, so if you've forgotten your unit circle, that's fine, that's forgivable. As long as you have a means of determining what the values of sine and cosine are for trig values that are in quadrant 1, that's the important thing. So like pi over 6 and pi over 3 are common angle measures that we use. And so this point on the unit circle over here with pi over 6, I have to go further in the x direction. So that's going to be root 3 over 2, 1/2. And then this one's going to be 1/2 root 3 over 2. Okay, so substituting, this would be 2, so cosine pi over 3, that's going to be the 1/2. Sine pi over 6, I'll tell you what, I'm going to mark them off like this. So cosine pi over 3 is 1/2. So that's going to change to 1/2, and that's going to change to 1/2. Sine pi over 3 is root 3 over 2. I think I'll just get rid of this for a second. I'll come back in a moment. All right, then sine pi over 6 would be 1/2. So that's also 1/2 down there. And cosine pi over 6 is going to be root 3 over 2, and this would be root 3 over 2. Okay, so simplifying, well, let's see, 2 times 1/2 would cancel, so it looks like I have 1/2 plus root 3 over 2 times root 3 over 2 would just be 3/4. And in the denominator, it looks like I have 1/2 times root 3 over 2, so that's root 3 over 4 minus, oh, no, actually, no, sorry, 2 times 1/2. I forgot about my 2. So that would be root 3 over 2 minus root 3 over 4. There we go. That's better. Otherwise, I would have gotten division by 0, which isn't a big deal. It just means you have a vertical tangent line, but I'd prefer not to get that. All right, so 1/2, we would need to change that into 2/4 in order to add those fractions. Down here to subtract, I'll say 2√3/4 minus √3/4. So that gives me 5/4 over √3/4. If I invert and multiply, that's 5/4 times 4/√3. So it looks like 5 over the square root of 3 is the slope of that curve. And that's how that would be done.